Wave-particle duality. The wave-particle duality means that for electromagnetic wave, it can behave both as a particle and as well as a wave. So the equations that wrap it up is lambda is equal to h divided by p, and h is your Planck's constant, p is the momentum, and lambda is your wavelength. So in short, if you actually have an electromagnetic wave of a specific frequency or wavelength, once you determine its wavelength, and you can use this formula to calculate what is the momentum of the photon. Vice versa, if you actually have the momentum or the kinetic energy of the photon, you can also work out what is the frequency or the wavelength of the photon. This is an experiment that is used to demonstrate that electrons behave as a wave. So electrons is being accelerated and passed through a thin layer of graphite. And in the process, you get actually a diffraction pattern as observed here. Let's take a look at the mathematical expression. So first, the kinetic energy of the electrons is your EV. V is the potential difference that's used to attract and accelerate the electrons. And that will translate into kinetic energy of the electron. From the kinetic energy, we can work out the momentum, which is 2mEV. Using the wave-particle duality equation, lambda is equal to h over p, we can find that the wavelength is governed by this expression. Using diffraction formula, whereby angle theta is approximated as wavelength divided by the slit separation. In this case, the slit separation is the distance between the graphite atom. That is actually equal to r, which is actually the radius of the circular diffraction pattern. And that is actually your theta. So d is the distance between the screen and the thin layer of graphite. So d is the distance between the screen and the thin layer of graphite. So using this equation and substituting lambda with this expression, which is here, all right, we're able to work out that the radius is inversely proportional to the voltage. In this experiment, it clearly demonstrates that electrons could behave like wave. And similarly, like what we observed in the earlier chapter on photoelectric emission, electromagnetic waves has particle-like behavior. This is a summary of the wave-particle duality. Light behave as wave. We can have interference of light, meaning to say we can have superposition, constructive and destructive interference. Light behave as particles. That is clearly demonstrated in photoelectric effect. Electron behave as particles. Electrons are part of atoms. And electron behave as wave. And that could be observed in the electron diffraction that we just discussed.